Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about math and science. And today we're talking about pH. This is the last unit for chemistry this year, for elements of chemistry. And they're trying to start testing. So we're hearing announcements as they're calling kids to go to take their EOCs. But we don't have one in chemistry, yay! All right, so what we're going to be talking about is acids and bases. And I think it's going to be pretty easy because most of this you already know about because you've lived life. You're wise, old 15 and 16-year-olds who've lived life and you know about acids and bases. Okay, so for our thing, our title is pH, acids, and bases. And it tells how acidic or basic it is. And you have a working knowledge of acids already. Now our math this time is this math formula right here. Is that the pH is something, and that's the scale we use to measure how acid or base something is equal to the negative log of the concentration. Remember those little square brackets mean concentration of the acid. And the acid can be shown as the concentration of hydrogen ions, or if you look down here, it can also be shown as the concentration of this H3O plus. That also shows the amount of acid, and that one's called hydronium ion, and I'll explain that to you in a second. So we're going to get to use that button on our calculator that says log. See, it's always fun when you get to learn something new about your calculator. What logs have to do with is in math, you can go and watch on my YouTube channel, you can go watch an Algebra 2 playlist where I explain about it more, the math of it. But what it has to do is it has to do with raising things to an exponent. So if you think about that, if you take 2 and square it, it's 4. And if you take 2 to the third power, it's 2 times 2 is 4, times 2 is 8. Everybody followed that mathematically? Everybody's got that in your head? 2 squared is 4, but 2 to the third power is 8. What do you do? What power do you raise 2 to get 6? It's going to be some weird thing, right? It's not a whole number. How we have mathematically answered that question has to do with the logarithms. And there's different kinds. There's the kind on your calculator that is the button that says log, and that is logarithms to the base 10. There are other base logs that you can tell your calculator if you have one of these TIs. You can do different bases on it. It's one of the reasons why you want one of those. TI-84 if you're buying. I think I'm buying this summer. My pink one that I love is starting to not charge anymore. They usually run them on sale for back to school for around $80, but I want the color one, so mine's going to be more like $100. But anyway, so there's that kind of log. There's base 10, there's other bases, and there's also something called natural logs, and there's another number like pi, which is E, and it's very less popular than pi. Everybody knows about pi and the 3.14. But so there's this whole little bit of math that y'all don't know yet that's very interesting and fun. And it's very satisfying. There's certain math that's really satisfying to do because you get to mark stuff out. So I would advise y'all, especially when you get to Algebra 2, go watch my video explaining it all, because it's really, it's fun and it's powerful. But what we're going to do today is we will be using the negative button. So like on my calculator, the negative's right down here, and we'll be using that button that says log. This is a base 10 regular, not natural log that we'll be using. And whatever I tell you the concentration of the acid is, you just put it in. You do negative log, put that concentration in, enter, and it tells you the pH. Now, the other thing though is there's another scale that we don't use as much, and it's called pOH. And it tells what the concentration or how much base something has. Acids and bases are opposites, and so it's not very common, but you need to know about it too. And then this is the big thing to remember, the other math thing. Oh, and pOH, if I give you the concentration of base, you just put that in your calculator too. Negative log of the concentration of the OH, that's what makes it basey, is going to tell you the pOH. And then if you have to get from one to the other, pH plus pOH is 14. I don't know why 14. I don't know who came up with this scale. Wasn't me. 14 seems sort of random, but it's 14. All right, so how do we feel about the math? That's the math right there. Not too bad? We can add to 14. We'll do practice problems. It'll make more sense. Okay, now let's talk about just our knowledge of acids. How do acids taste? Sour, yes. Lemon juice would be a good example of that. So they taste sour. We'll talk about other things. So there are different definitions of acids and bases. We have known about acids and bases for way longer than we knew chemistry. So people knew about acids and bases as long as there's been people. They've known about, sour citrus fruit and then bases being used to make soap. They knew about ammonia. Remember we talked about Amun-Ra, the god, in ancient Egypt and the human sacrifices and all of that. So they've known about bases. Ammonia is basic. And so they've had a hard time coming up with the chemical definition of what an acid or a base is. So there's different ones. There's Lewis acids and bases. There's Bronsted-Lowry. There's Arrhenius. So there are all these different definitions. And when you take Chem 2 with me year after, or AP Chemistry with me year after next, we'll learn more of these definitions. So it's not really going to be that much harder. It'll just be extra learning. You'll get to learn more electrochemistry. You'll get to learn more about acids and bases. You'll get to learn more about those solubility rules. Remember NAG-SAG and our pig? You get to learn more about those. But it's just more. It's not necessarily harder. Okay, so here is our first definition of what is an acid chemically, and it's that it has a hydrogen ion. And if you think about it, how many protons does hydrogen have? Remember that from our very first unit? How many protons does hydrogen have? One. So if it is lost its only electron, then it is just a proton. H plus is a proton. And that's why you have a drawing of a proton up there. See that proton on your notes? Because a hydrogen ion is a proton. So there's these protons floating around your solution. It's an acid. And another thing is that it might have a hydrogen that comes off, it disassociates. That's what we learned in our last chapter on water. So example of an acid is HCl. That's hydrochloric acid. We've used it in lab several times. We use 3 molar, we use 6 molar hydrochloric acid. And when hydrochloric acid is in water, it comes apart into these hydrogen ions and chlorine ions. And so it's a very strong acid. So another way to say this is it donates a proton. So an H plus is a proton. And that's the Bronsted-Lowry definition. Now, so here's an example of another way to look at it. If you have hydrochloric acid, that's an acid. And you add water. Now, this is the weird thing. Here, water is going to act like a base. In reality, water is neutral. But water is really made out of an acid and a base put together. So it can act like an acid or a base. And it's acting like a base here. Then you end up with this. This is called the hydronium ion. And that's the other thing that is considered the thing that makes it an acid. Those two, they're really two ways of writing the same thing. But this is called the hydronium ion. But here it's acting like this is the acid. So this is called the conjugate acid. And you would learn more about that when you take AP with me. Conjugate, it's hard to spell. It's the conjugate acid, and then this chlorine is our conjugate base. Now, these little conjugate acids and conjugate bases are not going to be on the test. I just wanted you to see it. I wanted you to know that this sort of exists. That there's this way of labeling what goes on in a reaction as acids or bases. That's your takeaway from this, okay? And then the other thing is this. You need to know that right there, H3O+, is the hydronium ion. So what it looks like, did I draw it on your notes? I meant to. What it looks like is you've got an oxygen, and it's bonded to 3 hydrogens, and it's got its one lone unshared pair. And overall, it's got a charge of +1. So that's called the hydronium ion. It's sort of like a water where an extra hydrogen cozied up to the unshared pair there and made it to be a bond instead. Because remember, 2 shared electrons is a bond. Okay? Y'all doing all right? Sort of following along with these ideas?
What is that called again?
There's the hydronium ion. It's that right there. Woo! It's more fun with sound effects. Can I roll up at least to that part where there's no writing? Good. All right. Now, what do you think acids react with? You have a clue in your drawings. What do you think acids react with? Not guitars, but what kind of guitar does it look like? It's a... No, it reacts with metals. That's supposed to be a heavy metal guitar from the 80s, some hair band, like Rat or Poison. Here's they react with metals. So if you put, one of the things that people used to do is if their battery on their car was corroded, they'd take Coca-Cola, because that's an acid, and pour it on the terminals to get it to react with the metal and clean it off. Has anybody ever heard of that before, to pour Coke on a battery? Also, like, just, they react with metals. So if you have acid on metal, it reacts. And we actually saw that in lab some. And then the other thing is we're going to be doing a lab tomorrow where we're going to look at a bunch of acid things and we're going to decide if they're acid or base. And how we do that is a variety of ways, but one of them is that we're going to use indicators. And one common indicator you could have used in elementary school is called litmus paper. Anybody ever used litmus paper before? It's little red and blue strips of paper. You dip it in it and it turns colors, and you can tell if something's acid or base. So blue litmus will turn red in acid. Acids have a pH, remember that's our scale of acidity or basidity, of 0 to 6.9. So let's think of some examples together. What are some examples of acids? You have clues in your drawings. There's stomach acid. Yes, your stomach acid is hydrochloric. And it's very strong, and that's why when you go to elementary schools, you see the carpet, they have these big bleached white places on it. It's because elementary kids barf a lot. And when they do, they bleach the carpet. It's one reason why I like to teach high school. Elementary kids, they still have bathroom accidents. They throw up. They're just kind of gross. Y'all are much nicer. Y'all don't throw up. You don't pee yourself. Y'all are just great. Y'all are great to teach. But yeah, that HCl is stomach acid, hydrochloric acid. What's something else that's an acid?
The stuff from cigarettes.
Like the tar and stuff in cigarettes?
I don't know. There's a cigarette drawing, so I was trying to...
That is not a cigarette. That is your litmus paper. So you need to color it blue with the end of it turning red. I can see that. It could be a cigarette being put out, but it's not. Do y'all know what those little faces are? They're called funny faces. Anybody know what they are? Yeah, this was the big competitor to Kool-Aid. Kool-Aid put them out of business, but they were called funny faces. And yes, one's a lemon and one's an orange. So what are some things that are acidic then? Citrus, yes. So things like lemons, anything citrus. What else do you notice there? What are the drinks that are there?
A Coke and then, I don't know, tea?
Yep, cola. Also tea and coffee. Most things we drink are acid.
Is milk? I would think so.
We're going to talk about milk. But we can do it now. Milk's pH is about 6.5. So milk is really, really close to neutral. So on the test, when I ask you what's the pH of milk, the answer is neutral. It's really close to neutral. So is blood. Blood and milk, those natural fluids. I mean, it's gross to think about, but milk is a natural fluid. Tears, all of those things are really close to 7. 7 is neutral. They are salty, but that doesn't mean it's acidic. Mm-hmm. Well, everything natural with our body is pretty close to neutral. And then notice we have a battery up there, so battery acid. Now, different batteries have different acids, but the one in your car is sulfuric acid. Sulfuric acid. Remember when we did our sulfur lab, how stinky it was? So the battery acid in your car is that. All right, so that's acids. So there'll be a lot of questions on the test. Is this an acid or a base? A lot of that you will learn tomorrow in lab when you test them. Bases taste bitter. You can remember that because bases and bitter both start with the letter B. But don't be confused. Coffee tastes bitter, but it's an acid. But just if you taste a base, it tastes bitter. It's not the only thing in the world that tastes bitter, but bases taste bitter. Do you follow that? Okay. They have OH, the hydroxide ion. It sounds like an Oreo cookie, doesn't it? Or the fake Oreo cookies, the hydroxys, you know what I'm talking about? But it's not. It's a base. And so the OHs come off. They dissociate in water. The Arrhenius definition is that it has this concentration of OH. So our classic base is sodium hydroxide. That's what you made in the volumetric flask in lab last week. Remember those little white pellets you put in the volumetric flask? You were doing this. You put sodium hydroxide in water and it dissociated. It was a strong base. There's another definition of it, that it accepts a proton. And the reason why is because there are bases that don't have OH, like ammonia. Ammonia is a base that doesn't have OH, so it can be something. And remember I told you, we've known about these things longer than we've known chemistry. How do bases feel? Any guess by looking at the pictures? Soapy, so they feel slippery. They're slippery. And they react with fat. So that's how you make soap. You take sodium hydroxide lye, you mix it with fat, and that's how you make soap. And it could be olive oil, like palm oil. It could be coconut oil if you're buying the fancy natural soaps. But that's how you make soap, is a base plus fat.
What about bleach?
Bleach is a base. Now, sometimes strong bases end up being dangerous because kids drink them and kill themselves or get brain damage. So one of the things they've started doing lately is they will pH balance, or they will add things to things that are naturally strong bases to make them safer. So a while ago I tested some bleach and it was neutral. And so someone asked me, what's the pH of bleach? And I said neutral. And then I thought about it and thought, no, it's not. It's a base. You can tell because it feels slippery. But the stuff I had tested had been pH balanced. Also, like shampoos should all be bases, any kind of soap. But a lot of shampoos, when you test them, they'll be neutral because they pH balanced them. They would think it's better for your hair, too, not to have like too much base on it. So this one does the opposite. It turns red litmus blue. And how you can remember this for the test is base and blue both start with the letter B. So on the test, when you start getting confused, just think about that. See, this is interesting, isn't it? It has a pH of 7.1 to 14. So in the middle you have water, which is neutral. Okay.
But aren't like some waters they like are
yes.
Like Dasani's like more
yes.
acidic
Pure water is 7.
Mm-hmm.
But there are movements in the health. And one of them is that there are like chiropractor types who think because most everything we drink is acid that we have too much acid and that we need more base in our diet. So they sell basic water where you can drink this water that's slightly basic. And there are diets where you try to cut out the acids and you eat more bases. And it's supposed to be good for you. I don't know. acids sure do taste good. All that oranges and stuff like that. So here are some examples we've already said. Ammonia is a base. Lye, which is our sodium hydroxide, our Drano. Soaps. Hair dye. You can tell because if you've ever felt of it, it's slippery. Slippery things. Now, strengths. You can have strong acids and strong bases. That's why we have a little strong arm on our notes here. There are also weak acids. Okay? The strong acids dissociate completely in water. And you can think of this, remember when we learned about equilibrium, that some reactions go to completion and others don't? This disassociation goes to completion if it's a strong acid. If it's a weak acid, it doesn't. These are more dangerous than weak acids, and they have a very low pH. Their pH is lower. The lower the pH, the stronger the acid. So hydrochloric acid is a strong acid. Citric acid is a weak acid. So it's safe to drink orange juice, but not hydrochloric acid. You would die. You would die. So here are some examples of strong acids. Sulfuric acid is battery acid. So make a little note of that. Yes?
Question. Okay, so you know at Yellowstone how like all the sulfur and like if you would step in it you would like burn? Is that because it's like acidic?
I don't know. I know that it's extremely hot, so that might be what burns you. But sulfur, remember how we learned it has different allotropes? And it depends on if the sulfur in Yellowstone is disassociating with hydrogens, then it would be acidic. But that would be interesting to find out. I've never thought about that. Do you know that there are some people who think Yellowstone's about to blow up and like we're all going to die? They say it's a super volcano, and that if it blows up, it would like take out the whole middle part of America, which makes all of our food. So that would be bad. And it keeps having all these tremors and stuff, so we need to hope it does not explode.
And it's like years, like you know, it's like it's supposed to go like every hundreds of years, and it's like overdate or something.
Yes. Yes. Yeah. Like they thought they had it figured out, and now it's not doing what we thought it would do. So, interesting science. Okay, so another one is hydrochloric acid. That's your stomach acid. So on the test, I want you to know that sulfuric is battery, hydrochloric is stomach acid. It's also sold if you go to Home Depot and want to buy some hydrochloric acid, they don't call it hydrochloric, they call it muriatic acid. And you're going to get that on a worksheet. But if you see muriatic acid, it's also in toilet bowl cleaner. It'll say with muriatic acid, and it's hydrochloric. Nitric acid, that's one that we've used in lab. Perchloric is another. Those are just some strong acids. So here's an example. We have hydrochloric and water making hydronium and chloride. So it's disassociating completely. And so you see our arrow only goes one way. It's disassociating completely. So now we're going to talk about the opposite, weak acids. Right there. So this is a strong acid, HCl, strong acid. Weak acids, examples are vinegar, which is a dilute solution of acetic acid, citric acid, lactic acid, that's the acid in milk that, some people can't handle the lactic acid. They have to drink the other stuff. What is it called? The easy to digest milk, lactate. Lactate. You might have to drink that. It doesn't taste very good. So it does not disassociate completely. So this is an example of a weak acid, and you need to draw the arrow going the other way too. Now, this is an organic acid, and I meant to draw this on your paper, and I don't think I did. Okay, so organic acids, see how these are natural things, vinegar, citric acid, milk acid. These organic acids have this on it. And it's a carbon double bonded to an oxygen, single bonded to an OH. So I say that it says Cu. Organic acids say Cu. So, and then they put an R there, and there's no element R on the periodic table. That R means you can have more carbons there. R stands for more carbons. Okay, so this is an organic acid.
What is this drawing supposed to be?
Let's see what we got.
The little box.
That's a battery with your battery acid in it. And we've got the strong acids can kill you. Oh, I do have the hydronium ion drawn there, and the organic acid. I did draw it in your notes. And the milk, lactic acid, Drano, that's the strong base. Okay, so strong bases versus weak bases. And it's the same thing. They dissociate. Oh, yeah, I got that one. They dissociate completely. They are more dangerous than weak acids. Now, which is more dangerous, a base or an acid? Nope.
No base.
Nope. We can't tell. It depends on which one it is. They are both corrosive. They will both kill you. They are both bad. They have a low pH. I said it wrong. They have a high pH. They're 7 to 14. And the higher the pH, the stronger the base. So there's our example of lye, a strong base, dissociating completely. So examples of lye, sodium hydroxide, potassium hydroxide, barium hydroxide. Notice they have this word hydroxide in it because the hydroxide ion is OH. Now, so how can you tell that something is a base or an acid? You do it with an indicator. It could be litmus paper, universal indicator, phenolphthalein. That's the one that was pink we used in lab. Hydronium papers, we're going to use those. Also, you can use a meter. I have a pH meter. We'll look at that tomorrow in lab also. So that's how you can tell. Now, I was going to tell you about how can you tell which is worse that we don't know. There is a thing now where terrorists will take a chemical and throw it in your face. And it melts your face, makes you go blind, and it can kill you. In some cultures, men will do this to women who reject them as a suitor. And you can go online, it's terrible, and you can see these beautiful girls whose faces got melted because they didn't want to go out with somebody. I just think it's horrible. Going down on a limb here saying this is horrible. So anyway, it's a thing. Well, it's coming more to the U.S. as we're getting more terror here. And it happened recently that there was a lady, she just went outside of her apartment, and this stranger, it wasn't a guy she had rejected or anything, threw chemical in her face, melted her face, she's gone blind, she lived. But I mean, she was this beautiful, healthy lady who's now blind and disfigured. So, we're going to talk about a little bit of acid-base safety. One is, we already talked about that kids get in, especially to the bases, and end up killing themselves or making themselves brain damage. So our first safety is child safety locks in all cabinets, right? Don't think your kid won't do it, because they will. As soon as you're not looking. What about if you don't have a kid? If a kid ever visits your house, you need to have the child safety locks on. If you're going to be the aunt, the uncle, the neighbor, the good friend, you just need to get those child safety locks. It's not worth the kid getting damaged over these chemicals under your sink. People put those cleaning chemicals, those strong bases, under their sink. So child safety locks. The other one is what we're going to talk about is what happens if you combine an acid and a base. What do y'all think happens if you combined an acid and a base?
Bomb.
Most people think a bomb or an explosion. But what you get instead is salt and water. That's why we got the beach there. Salt water. It's neutralization. So if you add the strongest acid, hydrochloric acid, with the strongest base, sodium hydroxide, you get HOH, which is also H2O, and NaCl, that's salt, isn't it? Now, it's not always NaCl, but you get salt and water. This is neutralization. So, you just walked outside. Someone throws a chemical in your face. You don't want to go blind and have your face melt. What should you do? You should try to wash it off, but regular water isn't going to do it. Salt water's not going to do it. You need the other one. You don't know if it's acid or base. You need to put the other one on your face. So, how do you tell which one it is? What do bases feel like? Slippery. If it's slippery, then you just got probably lye in your face, a very strong base. So you would need to grab vinegar, cola, grab ketchup. Tomatoes are acidic. Grab something acidic and get it on there as fast as you can while calling 911 and getting to the hospital. But while the ambulances are coming and taking you to the hospital, it's going to be too late. Okay? So bad acid, the opposite. Acids feel like water. Lemon juice is an acid. It feels like water, doesn't it? It's not slippery. So if it's an acid, then you go for a base. Grab the ammonia. Grab baking soda. Grab something to neutralize it. Wash it too. Use lots of water. But try to get that opposite on there as fast as possible to neutralize it. Does that make sense? So whenever I read about these in the paper and the person got disfigured and all that, it always hurts my heart that they didn't know their chemistry what to do quick enough to save it. I'm always like, they didn't pay attention in chemistry, or the teacher didn't emphasize what they should do quickly. Because people, quickly went to that lady's help, called 911. They didn't know what they really needed to do was start looking through the kitchen, find the opposite, and save her. But she went blind. So, and that's just terrible. Terrorism, terrible world we live in some ways. Okay, so what about water? Is it an acid or a base? It's neutral, and it can actually act as both. Let's see. It can be an acid and a base. It can act like an acid and a base because it's combined. It's water has got OH and it's got an H. Do you see how it's both? So it's made of both, so it's neutral. So this is H alone is an acid, OH is a base. Together they make water. Water has a pH of 7, and it's not an acid or a base, but it's neutral. Now it can act like either one sometimes, but it is neutral. Okay? Now pH, how we calculate it, and pOH. It's our scale. Can I scroll? That was all pretty easy, right? That was a lot at once. Okay, water can be an acid, and water is an acid and a base. It's made of both. H is the acid, OH is the base, water. So when things are acid, they're going to start with H. When things are base, they're going to end in OH. Because remember, we always put cations before anions when we write equations. Remember that unit 4 bonding chapter? So acids are not acid, water's not acid or base, but it's neutral. And we're going to say blood and milk is too. They're both slightly off, but they're basically seawater. All of those have similar pH. Okay, can I scroll now? Okay, now how do we do the math? It's not fun if we don't get to do math. Calculating pH and pOH. Acidity and basicity is reported on the pH scale. The formula is the negative log of the concentration of the acid for pH. And pOH is the negative log of the concentration of the base. So let's do it on our calculator. Everybody get out your calculator. Doing your calculator. Negative log 0.0235. Enter and see what that pH is. Wait a minute. I changed y'all's, didn't I? Hold on. I think I redid it and gave y'all different ones that are more fun to do. Oh, there it is. No, I left that the same. Those are just ones I wanted to try. Okay, did y'all get negative, well not 0.3 something?
How do you put it in?
Yep. Negative log and then 2.5. And it's negative 0.398.
Why is it 2.5?
Yours said 2.5. Oh, because I did I changed it. See, that was it. Let's erase. I decided that was a boring pH. We needed a better pH, and I changed it to 2.5. So now let's try that. Do negative log of 2.5. See how mine's different than y'all's? Is y'all's this or the 2.5?
It's that.
It's that. Okay. Do that one. No, y'all do y'all's. See, I changed it because I didn't like the numbers I had. So I want you to do the other one. Negative log. And that's what was confusing Mr. Myrick, and I wasn't understanding his problem. Now I do. 0.0235. There we go. So our pH is 1.6. All right, did y'all get 1.6 on your calculator? Okay, so what's your next one? What about, did you get 6? Did you try 6? Do negative log of 6 and see if you get, and tell me what you get.
Like negative 0.7?
No, I got 2.18.
Yeah, negative 1.7.
Let me try it. I might have done it wrong. Negative log of 6. I got negative 0.77. So, oh, so y'all don't have these numbers, right?
No, we do.
Y'all do have these numbers. I did the wrong one.
We have this everything that's up there.
Y'all have what's up there. So stop looking at my paper. Look at that. Okay, let me try it again. Negative log of 0.0065. It is 2.18. Okay. Okay, so the next one is negative log of 10 to the negative third. Did you get 3? Notice that when this is, that's the same thing as 1 times 10 to the negative third. Put that in also. Try the negative log of 1 times 10 to the negative third and see how it's also 3. So if something is just 1 or times 10 or 10, then the pH ends up being that exponent without the negative sign. It only works when it's like that. But if it's like that, you can know the answer. So now try that one. Now this one, this is the concentration of OH, but we put it in the same way. You just do negative log this number, negative log 0.0035, and you should get 2 point rounded up to 5. Is that what y'all got?
Yes.
Okay. And then the next one, it's you should get rounded up. It's like 4.3. Is that what you got?
Yes.
4.3. And then the last one should be 5.7 if you round it. 5.7. So make sure you can get those on your calculator. Now, pH plus pOH is 14. So this math is so easy, you can do it in your head. If pH is 3, what is pOH? 11, yes. So let's go back here. If pH is 10, pOH is 4.
Oh.
If pH is 8, pOH is 8, pH is 6. Now, so we could actually go back and figure it out with these too. If this is pOH and we wanted pH, we would do minus 14, take away the negative, and that would tell us our pH. Does that make sense to you? You'll get to practice your math. Okay, here's our last little concept. And it's always my goal in life to get to say this by the end of the year. If we do, that means that we did all right getting through what I wanted to. And this is something called redox chemistry. It's electrochemistry, so that's kind of fun. And it's how a lot of things are made. It's something that's very useful, and you've actually seen it. And how you but there's one little confusing word thing to it, and it's this. How you remember it, and it's because we have a lion there, is Leo the lion says grr. See how the lion is saying grr? So everybody get it in your head. Leo the lion says grr. I did not make this up. It's in every chemistry book. You can find the page where it says, how you remember this is Leo the lion says grr. I think we could have made up a better one, but this is the one, and we go with it.
It makes sense because Leo, the astrological sign, its symbol is a lion.
There you go. And he can say grr as well as anything else, right? Okay, so this is what it means. If something loses an electron, so Leo is loss of electron, it's called oxidation. So when something loses an electron, that is called oxidation. The loss of electrons is oxidation. Everybody good so far? Not too confusing so far. Leo the lion says grr. The loss of electrons is oxidation. Leo. But this is the confusing part. The gain of electrons is called reduction. I told you I didn't make it up because I wouldn't have called it this. Because we think of, if we are reducing, we're losing fat, we're getting skinny. No. In chemistry, if something gains electrons, it's called reduction. So that's where grr is. Gain of electrons is reduction. Now, what does this mean? Chemically speaking. Can I go on to the next part? Okay, here's our example. Here you have sodium. And remember from the periodic table that sodium is in that first family that wants to lose their kids, right? So the sodium is going to, when it combines with chloride, it's going to lose its electrons and it's going to give them to the chloride, which is going to gain the electrons. We learned about that right at the very beginning. The bad parents and the baby stealers, right? So this one loses electrons. The loss of electrons is oxidation. So this is oxidation. Let me see how I write it. So it's oxidized. This one gains electrons, so it's reduced. Why is it called reduced? We'll talk about more, but there's really not a good reason. I think maybe they were drinking when they named this. I don't know. It was a long time ago. It was probably the 20s. You know, they were wild in the 20s, those speakeasies and stuff. Okay, so